In 2019, Google's quantum computer did a 10,000-year task in 200 seconds. IBM immediately said they could do it in 2.5 days. Neither number was the point. The real story of quantum computers isn't a race. It's a quiet 30-year war against noise. And if you think they're just faster versions of your laptop, you've been lied to. Quantum computers aren't faster. They're specialized. Tools built for a few specific problems. And right now, they're mostly losing because of a single, stubborn enemy. Error correction. Think of a quantum computer like a broken toaster. It looks futuristic. It has wires and chips and a little blinking light. But when you try to make toast, it either shocks you, catches fire, or produces a slice of bread that is somehow both burnt and frozen. That's quantum computing in 2025, a very expensive, very cold, very sparking toaster. So, what is a quantum computer actually good for? Let's start with the basics. A normal computer bit is a light switch, on or off, 1 or 0. A quantum bit, a qubit, is more like a spinning coin. While it's spinning, it's both heads and tails at the same time. That's called superposition. And if you have two spinning coins, they can be linked so that flipping one instantly affects the other, even across a room. That's entanglement. Now, if you hear that and think, great, so it does everything faster, you've fallen for the lie. Superposition doesn't mean speed. It means you can explore many possibilities at once, but only for problems with a very specific structure. It's not a faster horse, it's a submarine. Amazing underwater, useless on land. The first person to prove this was a guy named Daniel Simon in 1994. He invented a puzzle called Simon's problem. Imagine a black box with a secret string of numbers inside. Your job is to guess the string. A classical computer has to try combinations one by one, like guessing a password by brute force. For a string of length n, it takes about 2 out n/2 tries. Exponential. Awful. A quantum computer, using Simon's algorithm, can ask a few clever questions and find the string in roughly n steps. Linear. Beautiful. A provable exponential speedup. The first real quantum advantage. But here's the catch. Simon's problem is a toy. It has no practical use. It's like proving your toaster can toast a single crumb faster. Congratulations. The crumb is toasted. The world is not changed. Fast forward to 2019. Google wants to prove quantum computers can do something, anything, that classical computers can't. They build Sycamore, a 53-qubit processor. They give it a task called random circuit sampling. It's basically generating a random number, but in a very complicated quantum-specific way. Sycamore does it in 200 seconds. Google's team then estimates how long the world's most powerful classical supercomputer, Summit, would take. Their answer, 10,000 years. They announce quantum supremacy. Headlines explode. The future is here. Then IBM, who also builds quantum computers and has a slight rivalry, says, hold on. Their engineers optimize the classical algorithm. They use clever shortcuts and disk storage instead of just brute force. Their new estimate? 2.5 days. Not 10,000 years. 2.5 days. The gap shrank from impossible to a long weekend. The supremacy claim didn't die, but it got a lot less supreme. It's like bragging your toaster can burn bread in 30 seconds, and then your rival shows up with a flamethrower that does it in 20. The flamethrower is absurd, but it ruins your record. This is the pattern. Quantum engineers build a weird machine. It does a weird trick. Classical engineers find a way to do the trick with regular computers. The finish line moves. Supremacy is a slippery word. It doesn't mean quantum computers are better at everything. It means they did one contrived benchmark that was hard to copy until someone copied it. So what does quantum advantage actually mean? It means solving the useful problem faster than any classical computer ever could. Not a toy problem, a real one. And the list of problems where we can prove a quantum speedup is tiny. Factoring large numbers, which breaks a lot of encryption. Simulating quantum systems, like molecules for drug discovery. Searching unsorted databases, thanks to Grover's algorithm, with a quadratic speedup. A few optimization problems. That's mostly it. For everything else, like loading your email or rendering cat videos, a quantum computer is not just useless, it's actively worse, slower, more expensive, and prone to errors. Quantum computers are not general-purpose machines. They're specialized instruments, like a particle accelerator or a space telescope. You wouldn't use the Hubble to take a selfie. You wouldn't use a quantum computer to run Excel. But even for those few quantum-friendly problems, there's a catch. A big, noisy, sparking catch. Right now, we are in the NISQ era. Noisy intermediate scale, quantum. Noisy means the qubits are unstable. They lose their quantum properties, a process called decoherence, in microseconds. Intermediate scale means we have maybe a few hundred physical qubits, not enough to do real work. Imagine trying to conduct an orchestra where half the musicians are drunk and the other half forget their instruments every few seconds. That's a NISQ device, a drunk orchestra playing a cacophony of errors. The solution is quantum error correction. But it's not like classical error correction, where you just keep a few backup copies of your data. In the quantum world, you can't copy a qubit. Physics forbids it. Instead, you spread the information of one logical qubit across many physical qubits. If one physical qubit fails, the others can correct it. The problem is the overhead. To get one reliable, error-corrected logical qubit, you need thousands of physical qubits. Thousands. For one, to run Shor's algorithm and break a modern encryption key, you'd need millions of physical qubits. We have a few hundred. We're not close. This is the error correction cliff. On one side, the NISQ devices we have now, noisy, small, mostly toys for researchers. On the other side, fault-tolerant quantum computers, machines that can run for hours without crashing, solve real problems, and maybe discover a new drug or a better battery. Between them, a chasm. And nobody agrees how wide it is. Some say 5 years, some say 5 years, some say 30. Some say topological qubits, a completely different kind of qubit that's inherently more stable, will save us. But topological qubits are still experimental. They're like a toaster that works in theory if you can find a material that doesn't exist yet. So where are we really? In 2025, quantum computers are real. They exist. You can even access some over the cloud. They're amazing physics experiments. They've taught us a lot about entanglement, decoherence, and the limits of computation, but they have not solved a single practical, economically relevant problem faster than a classical computer. Not one. The demonstrations remain in the realm of we did a trick. The tricks are getting better. The qubits are getting more stable. Error correction is improving, but the cliff is still there. When will quantum computers matter? They'll matter when we have fault-tolerant machines with enough logical qubits. Then they'll break some encryption, simulate some molecules, optimize some supply chains, but they won't replace your phone. They won't make your laptop obsolete. They'll be a weird specialized coprocessor for the hardest problems. A quantum accelerator, not a quantum computer, on every desk. Let's zoom out. Quantum computers aren't faster, they're different. They exploit superposition and entanglement to solve a tiny set of problems in ways classical computers can't. The first proof of this was Simon's problem in 1994, a beautiful but useless result. Google's supremacy claim in 2019 was real but fragile, undercut by better classical algorithms within months. The real bottleneck is noise. Qubits are delicate. Error correction is brutally expensive. We are years, maybe decades, from a machine that can do useful work. And that's okay. Science is slow, the headlines are fast. The broken toaster is still sparking. But one day, after a lot more physics and a lot more engineering, it'll make a perfect slice of toast. Just one very specific, very expensive slice. And it'll be amazing.